2 Thursdays now start the Cauchy integral in some detail. I left out the Paley-Wiener measure and integral and the Feynman integral, basically because they're just too damn complicated. If you want to read about them, be my guest. But it's need to know a little physics. It's just actually, according to Burke here, the Paley-Wiener integral and the Feynman integral are both some cases of head stop first one. Anyway, got to stop somewhere. Here's an idea. Let's see if investigate this. This is an idea to Tom Apostle at Caltech. This is called the Slavovian integral. Because in mathematicians from Slavovia are lazy, and they only like to use rational numbers. They don't like irrational. So they like to try to do integrals by recasting the Riemann theory only in terms of partitions that have to do with rational numbers. They only evaluate functions of rational. Can you prove some theorems about the Slavovian integral? Is it equivalent to the Riemann integral? Let me do it. What time is it? I got 3 minutes. Let's try to integrate from 0 to b. Let's try to integrate f of x equals x squared. Okay? So I'll chop this up. You can then try this with a Slavovian definition. Chop this up into n pieces. So the width of any piece here would be b over n, right? And if I'm at a particular point, kb over n, then this would be k squared b squared over n squared would be the height of the graph, right? So for example, if I do a Cauchy integral, that would be from the left. I won't do the Slavovian one, I'll do the Cauchy integral from the left. So I'm going to constantly be underestimating, but then I'm going to let n go to infinity and see what we get. So I'm using the left endpoint as an estimate of the height of the graph, and then I'm multiplying with a base b over n, right? I'm adding them all up. Okay, so let's do that. What's the area of a typical rectangle? This one that has height k squared b squared over n squared. I think I would k squared b squared over n squared. That's the height. And the base is b over n, right? Height, width. True? Okay. And then we want to add these up. K goes from, what, 1 to n? If I'm using the left-hand side, it really goes from 0 to n minus 1. Right? If I'm using the left-hand side, the first rectangle has no height. And then I'm 1 unit over. I'm over b over n. So I square that across. So what is the limit as n goes to infinity of that? Well, as n goes to infinity, so does n minus 1. And there's no contribution at 0. I might as well start again. Okay. So what I have to do is find the limit as n goes to infinity of the sum from 1 to n of, what is this, k squared b cubed over n cubed, right? Now, let me refer you to a previous course where we found the sum of the cubes from 1 to n. What it was? I think it's n times n plus 1 times 2n plus 1 over 6. That seem reasonable?
That's the sum of the squares.
Yes, squares. I said cube. This is a cube of n, but it's a sum of the squares. You know, 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 up to 1 over n squared is that. Right?
I think that's just 1 squared plus 2 squared.
The S is
And it's 1 plus 4 plus 9 plus 1 n squared. Yes. I've screwed myself up. The n's downstairs here, these are really k's. Because right now it's k. That's what take me out here. That's all true. Okay. So the sum of the first k squares is this, I believe. I'm pulling that out from deep memory. That's not even in RAM. That's in hard disk. It's somewhere down here. I'm getting flaky. So I factor out things that don't involve k. Sorry, okay, one n. You're going to let n go to infinity out here. Let this n goes to infinity. And we just decided that's b cubed over n cubed times. The sum of the k squares is, if I go up to n, is n times n plus 1 times 2n plus 1. So we want the limit as n goes to infinity. This is kind of sloppy of that. That is the limit as n goes to, I'll write it nicely here. b cubed times over 6. Forgot the 6. I'll put one of the n's under that n. I'll put another n under this n, and I'll put the final n under that one. So as n goes to infinity, this goes to 1, this goes to 1, this goes to 2. The whole thing is over 6. So I have b cubed times 2 over 6 is equal to b cubed over 3. Guess what? That just then looks like the integral, doesn't it? I can't see everything here. Oh, I'll write b cubed over 3. Is that the integral of this function or what? Yes. Okay. So there is kind of another justification. This is not quite the Fermat integral that we did the other day. This would be the high school calculus book integral of the squaring function. Let's see if you can prove a theorem about the Slobovian integral here. You're only allowed to pick rational points for your partition, and you can only allow the function to be evaluated as rational tag points. My question is, where does the Slobovian integral and the Riemann integral converge? Or should we just all be doing the Slobovian integral? You realize that Slobovian is kind of a joke. Okay, I just didn't want you to think, oh, who is that? It's nobody. Right. Slav. Lower Slobovian. All I can think of is the Dilbert country, where they're all up to their elbow or up to their knees in sheep dung. You know, what's that country where they outsource everything at Dilbert's company to this place where they're up to their knees in sheep dung all the time. Everybody walks around and they can only see their knees up. Elbonia, right? You guys don't pay attention. Okay. Listen, it's later than you think. Okay.
All right, see you next week.
See you next week. The rest of you, would you kind of...
Sharks.
Huh?
Sharks.